So there's our velocity of the water as it comes out of the rocket as a function of the gauge pressure, the difference between the pressure of the fluid and the atmospheric pressure.
Whoa!
And I know I was saying P final earlier, but this is the pressure of the fluid in the rocket, of the gas that we've pressurized with our bike pump. And then we know that the volume rate of change of gas in the rocket is going to be the flow speed of the fluid times the cross-sectional area of the nozzle. We talked about that in the previous video. So this is the volume of that tube, like a jet of toothpaste coming out of the rocket. It's a jet of water, which you saw in the videos. We get those streams, at least early in the flight. So that's A times the expression we had for UF, which is this square-rooted expression. So we know the change in volume, the rate of change of volume. We could just multiply both sides by dt to get the actual change in volume per step if we advance this equation in a code. So that's going to look like dv is just dt times the area of the nozzle. This is not the cross-sectional area of the whole rocket, but just the nozzle, times the square root of 2 over the density times the gauge pressure. And the change in mass of the rocket, which matters, it gets easier and easier to push the rocket because it's getting lighter and lighter all the time. That's just the density of water. This is rho H2O, times that change in volume, which we can calculate here. And then finally we have our rocket equation, and we have an expression for V fuel. We saw that expression for U using our expression from Bernoulli's equation, and we have this mass flux, this change in mass, dm, which we get from the change in volume.
Yeah. The numbers all go to 11.
So that's all we need to explain all of the motion of the rocket, and these equations are vectors, and we can worry about the direction later. But these are all the things we need, and if you keep it one-dimensional, it's pretty simple. Doesn't look simple.
Whoa!
But it's not too bad if we take it a piece at a time. So what is our numerical recipe for advancing the state of the rocket? Well, we're going to update the pressure and the volume of gas in the rocket. We're using our adiabatic equation of state and our Bernoulli equation. So we say that P gas is P initial times the ratio of volumes, and here V of I in brackets, we're keeping track of this as a function of time in our code. We're raising that ratio to the gamma, that's the adiabatic exponent, 1.4, minus P atmospheric, 101.3 kilopascals. That's just the standard pressure. And then we're going to advance the volume.
Yeah. The numbers all go to 11.
The volume at the next time step is going to be what the volume used to be, plus dt times the area of the nozzle times the square root of that expression we talked about. Now we're going to update the mass next. dm is just the density of water times the change in volume, which we just calculated. And then the mass is going to be what the mass used to be, plus that dm, that change in m. And then finally, we'll use the rocket equation, which is just Newton's second law, to find the acceleration a. So that looks like the new a is going to be 3 terms, this 2pga minus 1/2 rho cd squared ar ui squared. And let's identify those terms. And then a final term, just g, the weight of the rocket. So we've got thrust, which is caused by the pressure of the gas pushing through this nozzle. Pressure is force per unit area times area gives us a force. And we're dividing by mass, remember? So force divided by mass gives us the acceleration we're looking for. This is the full expression for the Rayleigh drag that we talked about 2 videos ago. Notice it has a form that looks like an energy. We've got a velocity squared. We've got a density, so it looks like 1/2 mv squared. That's the drag term. And then finally we have the weight of the rocket. So those are the 3 causes of rocket motion: thrust, drag, and weight. Here we've accounted for all of them, and we have a step-by-step way to advance the rocket through time, and that's all we need.